Hello folks, today we're going to look at exponential modelling. Let's go! So just to recap the work for today, for 25 minutes or so I want you to watch and copy through these examples. We're going to look at 2 examples and talk a little bit about exponential growth and decay. Then I'd like you to try exercise 14C, which is on page 318. I'd like you to do questions 1, 2 and 4 and obviously check your answers. Give yourself 25 minutes for that. And final 20 minutes I'd like you to try the attached exam questions. So I've stuck a PDF on the assignment and then check the mark schemes. Makes sense. Don't forget you have a homework that is due in by Sunday of those questions that were set on Wednesday. Let's go. So broadly speaking, there are 2 types of exponential model we might want to consider. The first one of those is exponential growth. And now we get exponential growth whenever we have an exponential, obviously, that's raised to some sort of positive power. So for example, if I have y equals e to the 4t, that would give me a graph that starts at 1 when t equals 0, because obviously anything to the power 0 is 1, and then increases massively past that. On the left hand side, it's obviously not having much happen. When you drew the graph of e to the x, this is exactly what you got. And normally, if we're talking about things that are exponential, we're talking about populations of things. And the key thing is obviously that not just that they're increasing, but the rate at which they're increasing is increasing as well. So human population growth probably has started to tail off in the last 10, 20 years, but has been following an exponential curve for the last maybe 200, 300 years. If you have like bacteria in a petri dish, they will go through an exponential growth phase where they're increasing massively before that sort of levels off and goes down to logarithmic and then decreases. And slightly more depressingly, I suppose, one of the scariest phases of the COVID pandemic back in April was the exponential growth phase, where not just the number of cases was increasing, but the rate at which the number of cases was increasing. We can kind of see this in the Liverpool figures at the moment. We've had a brief sort of, I suppose, exponential increase across the first half of September. Yeah, hopefully that works out. So let's look at some examples. So we're going to do the traditional rabbits on an island population thing. You'd be amazed how much math this has created. The Fibonacci series is based on how many rabbits are on an island as well. That's exponential. So we've got this model that the number of rabbits p, t years after their introduction, is modeled by p equals 80 e to the third t. Okay, so let's go through these one at a time. First off, how many rabbits were introduced? So if we ever talk about an initial amount, that's talking about when t equals 0. So all we have to do is substitute that into the equation. So we'll get p equals 80 e to the 0, that'll be. E to the 0 is 1, so p is equal to 80. In general, whatever this number is in front of the exponential function, that's your initial amount. Well worth remembering that. So how many rabbits were introduced when t equals 0? 80. Okay, part B, we want to sketch the graph. Now, we're only interested in t greater than 0, so we don't really care about negative t. We do know that it starts at 80 rabbits, and then exponential growth in general just looks like that. That's all you need to do for your sketch. What about C? How many years until the rabbits exceed 1,000? So, what we want to find is when the population, which is p, is equal to 1,000. And we know that the population is equal to 80 e to the third t. So what can we do with that? Well, the first thing we could do is you could divide both sides by 80. Don't be tempted to take logs. We can only take logs when it's e to the power of something on its own. So if we do 1,000 divided by 80, we'll get ourselves to a slightly more wieldy equation. 12.5 equals e to the third t. Okay, what would you do from there? Well, we now do have e to the power of something, so we can take our logs, and because it's a power of e, we want to use ln here. So we'll say ln of 12.5 is equal to a third of t, and then we can times across by 3, and we can say 3 ln of 12.5 is equal to t, and then we can type that in to actually get a value for that. So that gives us 7.58. So how many years until the rabbits exceed 1,000? Well, we could say 7.58, but we tend to want to say this in whole amounts. So we could say 8 years. Another option would be you could change that to years and months. So that is roughly 7 years, 7 months. It's slightly more than half, isn't it? Okay. Part D, rate of increase. Okay, if you ever see rate of increase, that's dp by dt. Let's write that a little bit better. That is dp by dt. And the general thing that you want to use for that is that if we've got an exponential function, if y equals e to the kx, for example, then dy by dx is ke to the kx. So let's apply that then. So for d, what is the rate of increase after 10 years? So we want to find dp by dt. Now p was equal to 80 e to the third t. So according to that little rule, we just need to do a third of 80 e to the third t. So we could simplify that slightly and say 80 over 3 e to the 1/3 t. But it wants the rate of increase after 10 years. So we need to sub in t equals 10. So we're going to do 80 over 3 times e to the 10 thirds. This is going to be quite a big answer, I think. Yeah, so that gives us 2,242.5 rabbits per year. That is not the amount of rabbits, that's how fast they're increasing. Every year is adding 2,000 more rabbits. So yeah, exponential growth gets pretty big pretty fast. Okay, 2 more to go. E, what is the population when the rate of increase is just 50 rabbits per year? So we know this is going to happen fairly early on. So if the rate of increase, that's dp by dt, is 50. So we need to say dp by dt equals 50. Now we've got an expression for dp by dt because we worked it out just in the previous question. So we can say that 80 over 3 e to the 1/3 t equals 50. And then we've just got to solve this and find what t is. So we would have to times by 3, I guess, and divide by 80 to get rid of this 80 thirds, or you could just divide by 80 thirds, I suppose. And that would give us that e to the 1/3 t is equal to 1.875. And then we take logs of both sides like we did on part C. So we'll get that 1/3 of t is equal to ln of 1.875 times by 3. So t is equal to 3 ln of 1.875. This should hopefully be a reasonably small number. Yeah, and we get there that t is 1.8858 ... kind of goes on. Have we answered the question? No, not quite, because it actually wants the population. So we found the time when that happens, and what we need to do is we need to substitute that time into the general formula. So we know p is 80 e to the 1/3 of t, so we need to sub in 1.8858 ... into that equation. And we'll get with that actually quite a nice number, that the population is 150 rabbits. And that kind of makes sense because if you look at the difference between the population and the differential, they're times by a third in this case. Like if we go from p to dp by dt, we're just times them by a third. So the rate of increase is always just going to be a third of whatever the population is. So we could have just times by 3. Finally, F, and this is an important question. Is this a valid model for all t? So if we increase t to a massive amount, does this still make sense? We know it obviously doesn't apply for negative t, but the model does say that. Well, what would happen, say, if t equals something ludicrously large, like 1,000 years after we introduced these rabbits? How many rabbits would there be? Well, let's just find out. So p is equal to 80 e to the 1,000 over 3. Have a guess about how big this is going to be. So if I stick that into my calculator, I essentially get a maths error. I get a number that is clearly bigger. It's clearly bigger than the biggest number of rabbits than 10 to the power of 99. You know, there are more rabbits at this stage on the island than there are atoms in the universe. So our solution for F would have to be something along the lines of no for large T rabbit population will slow down, I suppose, or will stop increasing. Either that, or we've really got to deal with these first 80 rabbits better. Okay. So the flip side of exponential growth is what we'd call exponential decay, and you can see the general graph what that would look like here. Exponential decay is when something starts at a high value and then decreasing at a sort of gradually decreasing rate. So the traditional one for this, and something that you might do in physics, is radioactive decay. You've got the idea of the half-life, where every however many, so this is every 20 hours, the amount of material turns in half. So we get 50% after 20 hours, we've got 25%. After 40 hours, after 60 hours, we'll have about 12.5%, etc. But you can also have things like the temperature of something in a room that is cooler than it. So the temperature of your cup of tea will follow an exponential decay curve. The value of a car after a certain amount of years will follow an exponential decay curve. So let's actually look at an example of this. So let's consider the amount of drug in a bloodstream. This is a good exam question that we found here. The amount of drugs in the bloodstream is represented as x equals dE to the minus 0.125 t, where x is the amount in milligrams and d is the initial dose in milligrams. And we've given an initial dose of 10, so we can definitely say d equals 10. So A, find the amount of drugs in the bloodstream after 5 hours to 3 decimal places. So that's just a case of substituting some things into the equation. We're going to use that D equals 10 because that was the initial dose. We're going to use T equals 5 because that's the amount of hours. And we're going to get X is equal to 10e to the minus 0.125 times 5. And we'll get that at that time, the amount of drugs in the bloodstream is 5.353 milligrams. Remember your units, make sure you round to the amount of decimal places they say. Okay, second question. A second dose of 10 milligrams is given after 5 hours. And we want to show the amount given after 1 more hour is 13.549 milligrams. So how do we do this? So what we've kind of got to figure out is how much drugs there are in the system once this second dose is given. Now we know that there were 5.353 from the initial dose, and then we added another 10 to that. So for B, we're starting with an initial dose of 15.353 milligrams. Okay, so we need to show the amount after 1 more hour. So we're going to need to just do X is equal to 15.353, that's our initial dose, times e to the minus 0.125, and then we're talking 1 more hour after that, times 1. And that will give us that after 1 more hour, we are down to 13.549 milligrams. Sketch the graph of this. Now this is an interesting question. So what would the whole thing would have to be something like, should really be a lowercase t, sorry. So we'll have our initial dose, which is 10 milligrams. We know that by the time we get to 5 hours, that's roughly gone in half to this about 5.3 situation. And then it's spiked up again. So we'll have an exponential decrease. And then we'll have, obviously this will now go up to about 15 milligrams. So we'll just have a vertical line going up to there. And then we'll have another exponential decrease. So roughly speaking, that's what our graph would resemble. It's kind of an exponential decay and then a sharp jump and another exponential decay. Okay, so at t hours after the second dose, there are 3 milligrams in the bloodstream. I want to find the value of t. So we're going to take what we said before. So we're still using now the initial dose is 15.353. And we want to find the value of t. So we're going to say that x is 15.353 e to the minus 0.125 t. And that is equal to 3. And we want to try and solve this. So what would our first step be? Well, our first step would be to divide by that 15.353. Our second step will be to take logs of both sides, so minus 1.25 t is equal to ln of 3 over 15.353. And then we'd want to divide by minus 0.125. Incidentally, that is minus 1/8, so you could also think about this as timesing by minus 8. But in the interests of keeping sensible, let's just do it like that. By the way, that 15.353 is absolutely right for people getting the 3s and 5s confused. So stick that in our calculator and we'll get ourselves to a value of just over 13, so 13.06. So we can say that this was 13.06 hours is our value of t. Cool.